will now be recorded.
Ganesh Charanam Gajanana Deval Munivar Panihum Dayakara Shri Ganesh Charanam Gajanana Deval Munivar Panihum Dayakara Shri Ganesha Charanam Nagabaranane Nanmare Potrum Nagabaranane Nanmare Potrum Namane Pranavagupane Jaya Shri Ganesha Charanam Gajanana Devar Munivar Panigum Dayakara Shri Ganesha Charanam Padam Nambum Ramadasa Varadane Modaka Priyane Gauri Sutane Padam Nambum Ramadasa Varadane Modaka Priyane Gauri Sutane Adidevanun Innerul இல்லை என்றார் ஆதிதேவனும் இன்னருள் இல்லை என்றால் வேதனும் வாழும் செய்தொழிலுண்டோ வேதனும் வாழும் செய்தொழிலுண்டோ ஸ்ரீ கணேச சரணம் கஜானன தேவர் முனிவர் பணியும் दयाकर श्री गणेश चरणम
Thank you, Nityashree. I now call my beloved HOD, Dr. Ann Hsiung, to present the welcome address.
Good morning to Anandal present here. Dear participants, we welcome you once again for our seminar. And today's keynote speaker is Dr. Pao Ann Hsiung. Sir, thank you so much for sparing your time with us. And some profile about Pao Ann Hsiung, sir. So he has completed his PhD and received his BS in Mathematics and PhD in Electrical Engineering from the National Taiwan University, Taipei, Taiwan, in 1991 and 1996 respectively. And he was a postdoctoral researcher at the Institute of Information Science Academia, Sinica, Taipei, Taiwan, from the year 1996 to 2000. He started his career as assistant professor in the year 2001. Now he is the director of Smart Living Technology Research Center, National Chancellor University. In addition, he is the Deputy Director of Taiwan India Joint Research Center on Artificial Intelligence, National Chancellor University. Dr. Pao Ann has published more than 279 papers in the international and national conferences. He was the recipient of 2010 Outstanding Research Award given by the National Chancellor University to 3 faculty members only. He received the 2001 ACM Taipei Center Hu-Ting Li Young Researcher for his significant contributions to design automation of electronic systems. He was also a recipient of 2004 Young Scholar Research Award given by National Chancellor University to 5 young faculty members per year. He received several advisor awards for Best Master Thesis, Embedded System competitions, and RFID design competitions. He helped the Chiayi city to achieve 2018 Top 7 Smart City in the Intelligent Community Forum Worldwide Competition. He has also helped obtain huge financial budget in the amount of NT $300 million And Dr. Pao Ann is a fellow of the IET, a senior member of IEEE, a senior member of ACM, and a life member of IICM. He has been included in many professional chapters, and the list continues. Dr. Pao Ann is the editor-in-chief for the software engineering topic of International Journal Advancement in Computing Technology, and the list goes on. Something is Advanced Institute of Convergence IT, and the editor-in-chief of the Automation Control System topic of International Journal of Intelligence, Information Processing, Human and Science publication in 2011. He is the editor of Scientific World Journal, Hyundai Publication Corporations, and the list continues. And he is an associate editor of Journal of Software Engineering Academic Journal, inclusive USA, and editorial board member of Open Computer Science Journal, Bentham Science Publisher Limited, USA, and international editor board member of the International Journal of Patents. Dr. Pao Ann has been on the program committee of more than 232 international conferences. He served as organizer, program chair, steering committee member for more than 50 international conferences. He has taken on active part in paper refereeing for international journals and conferences. Dr. Pao Ann's main research interests include reconfigurable computing and system design, multi-core programming, smart city technology such as smart traffic and smart grid, cognitive radio architecture, system on chip design and verification, embedded software synthesis and verification, real-time system design and verification, hardware software code design and co-verification, and component-based object-oriented application frameworks for real-time embedded system. Sir, I have never seen such a big profile in my lifetime. Thank you so much, sir, for gracing this occasion with your presence. Now I welcome you to give away the keynote address. Thank you, sir. Sir, not audible, sir. Kindly unmute, sir.
Okay. Is it audible now? Hello. Can you all hear me?
Yes, sir. Yes.
Oh, yeah. Okay. Okay. Thank you, Dr. Ananthi, Head of Department of Information Technology at Easwari Engineering College. Thank you so much for the very detailed introduction, and I'm very happy to be here to share our research results with you all. And I'm also very thankful to Dr. Kanaga Subaraja for the invitation and for convening the whole conference. Thank you, and welcome all the participants to the talk. This talk, let me just first share my desktop with you. Please wait for a moment. Okay, can you see my
yes, sir.
My screen? Is it fine? Let
yes,
me
sir.
just enlarge it.
Fine, sir. We are getting.
No, this I'll have to. Yeah. Okay. So the title of the talk will be on deep neural network-based data reconstruction for landslide detection. Actually, this is a work that was completed around 2 years back by one of my master's students in his thesis. I think he did a very good job. So that's why currently during these days, I'm using a part of his work on how we developed data reconstruction methods based on deep neural networks. So the method itself is not actually specific to landslide detection, but I'm using landslide detection as one of the applications. So if you have any data reconstruction issues like missing data in wireless sensor networks, so irrespective of what the application is, as long as it's a wireless sensor network and as long as you have data missing, you can always use this technology for deep neural network based data reconstruction. Okay, so let me go into the slides. Basically, we'll be giving a brief introduction to the background and then the motivation, and we will also talk about how we develop the whole system, which is called spatio-temporal heterogeneous data reconstruction, and then we'll give you some experiments and the conclusions. Okay, so as we all know that landslides occur all around the world, especially in areas such as mountainous regions and wherever there are lots of rainfall. And we all know that landslides, whenever they occur, they create a lot of disasters, and I mean, lives get lost, and there are many casualties. Even houses are damaged and all. So from this slide, as you can see, basically there are a number of landslides. Like in Taiwan, we have around 11.75 landslides average per year, and we also have casualties like 10.33 casualties per year. And the number of houses, of course, is much larger. We have more than 82 houses damaged per year. So if we can do landslide predictions or detections at an early stage where we can do some warnings and all, then of course the whole system will help early evacuation of the people. Okay, so landslides generally can be caused. There are lots of occurrences or different factors in which that affect the occurrences of landslides. Like here we have soil, slope, and rainfall, which are the main factors that affect landslides. So for soil, we have the depth of the soil, the density, the moisture in the soil, the transmissivity of the soil, etc. I'm sorry, I think the slides are running on itself. Okay, so we have the gravity, which affects which is actually the slope of the soil, which also affects the landslide. And for the rainfall, we have the intensity, duration, and the amount. So these are the factors which mainly affect landslides. To detect or to predict landslides, we are using the concept of cyber physical system, which is CPS in short. As far as the cyber part is concerned, basically it's a dual model of the physical system. So the mountainous region, wherever we have placed sensors, that is the physical system. And of course, we have the cyber part, which is a model of the physical system. So that's why we call it as a cyber physical system. In this case, we are trying to reconstruct the model of whatever sensor data we have collected in the physical system, from the physical system, and then we reconstruct the model in the cyber part. So in the cyber part, we can have AI algorithms, control algorithms, etc., which actually model the landslides which might occur. So this is a cyber physical system. As you can see on the left-hand part, we have the physical components and environments. On the right-hand part, we have the control algorithms for landslide predictions. And at the bottom, we have embedded sensor platforms, including the different devices like the soil moisture device, etc. Okay. Actually, there are three different kinds of methods which can be used to detect landslides. The first one is GIS, Geographic Information Systems, which collect and store, manage data, geographical data, and based on the geographical data, by analyzing them, we can predict if there are landslides in some particular areas. And then we also have computational intelligence like support vector machines, Bayesian networks, neural networks, random forests, genetic algorithms. These are all the different methods which can be used to do landslide predictions. The third class of methods are called physical models, which is like ShellSTAP is one of the models. We have SynMap, TRIGRS, Flip model, etc. So these are all the physical models which are generally used for predicting landslides. By physical model, we mean that we actually measure the different characteristics of the soil, the rainfall, the slope, etc., and then we come up with a model. Like in this work, we are using the ShellSTAP model, but we are trying to reconstruct the data which is used for ShellSTAP. Okay, so what is actually the ShellSTAP model? Actually, in this model, we have a metric called the factor of safety, FS in short. The factor of safety, there's a mathematical formula for that. But before going to the mathematical formula, from this slide, you can see that there's a slope and there's soil on the slope. And whenever there's rainfall, there's moisture in the soil. So the main concept behind landslide prediction in the stair-step model is that based on how much force the slope or the region, the area, the land can bear or endure, and based on how much force we are actually exerting on the slope. So if we are exerting more than the force that can be endured by the slope, then of course we have a landslide. So that's the basic concept. Of course, by increasing the vegetation cover, making the soil more rigid, there are lots of ways in which you could prevent landslides. But basically, when we are trying to detect if there's a landslide, we check how much force we are applying on the slope and how much force the slope can actually endure. So coming to the mathematical formula, as you can see, Fs, the factor of safety, is a ratio. On the numerator, we have the amount of force that the slope can actually endure, and in the denominator is the amount of force that we are exerting on the slope. Okay, so whenever we have the amount of force that is the denominator that we are exerting on the slope is more than the amount of force that can be endured, that is the denominator is greater than the numerator, then of course Fs becomes less than 1. And in that case, whenever Fs is less than 1, this metric is less than 1, we have landslide. There are many different factors which we have to consider, like C is the effective cohesion of the soil, the rainfall intensity, the soil transmissibility, all of those factors which are given at the right hand side, at the bottom right of the slide. So we have different characteristics of the soil, the rainfall, etc., of the slope, etc. Basically, most of the characteristics are quite stable as far as a particular region or slope is concerned. But we might have some of the characteristics which change drastically whenever we have rainfall, like the amount of rainfall, the rainfall intensity, like the soil moisture in the soil. These are all the factors which actually change rapidly whenever we have rainfall. So whenever we don't have rainfall, the probability of landslide is very low. But when we do have rainfall, the probability goes high. So whenever we are using sensors to do landslide detection, or we are using this kind of physical model to do the estimation of whether the landslide is going to occur, basically we are trying to monitor the rainfall intensity and the soil moisture. But of course, the slope also affects the whole thing. So in this work, we are mainly considering the soil intensity, the rainfall intensity, the soil moisture, and the slope gradient. Okay, so what exactly is the target problem that we are trying to solve in this work? Basically, whenever we have wireless sensor nodes in a wireless sensor network, there's always a problem of missing data because due to lots of different reasons, maybe the electrical power of the sensor devices have gone out. I mean, the batteries are out of charge. We don't have enough charge in the battery, so the sensors cannot send the data. Or maybe because of the big rainfall, the intense rainfall, the data communication becomes very poor. There are lots of different reasons where in a real actual wireless sensor network, the data is missing. There are lots of a big percentage of the data is often missing. But as far as this application is concerned, we know that this is a safety critical application where if the system fails, then we won't be able to predict whether there's any landslide. So in this kind of application, whenever we have the system, the target of the system is a safety critical application, and we need the data to be actually present for computation, for any kind of estimation, then we need to do data reconstruction. Of course, there are many simple methods in which data could be reconstructed. That is, we are doing reconstruction for the missing data. There are many, simple methods like linear regression or linear interpolation. These are all simple ways in which we could do data reconstruction. But if the application itself is safety critical, then there's always a problem as to how accurately you can reconstruct the data. Suppose the error in the data is quite large, then even if you reconstruct the data, the error in reconstruction is large, that even if you reconstruct the data, you're not sure as to how much confidence you have in the final prediction because the error keeps propagating. So if we have, like, for example, 1 or 2 sensors out malfunctioning, not working, or if you have more sensors not working, then all the error propagates, and then the final predictions of the landslides of any safety critical application becomes not trustworthy, or it becomes just not, I mean, you cannot use that result for doing any prediction. So that's why missing data is a big problem in wireless sensor networks. And here we are trying to use neural network based methods. We'll show you how I mean, why exactly we are using neural network models. Okay, so this slide is talking about why we are having sensors, the data from the sensors not actually reaching the control system or the cyber physical system, and what if the data, there's a big data loss, actually it results in safety concerns. Okay, there are many different ways in which you could do data reconstruction. Like I just said, we can use the relevant neighboring nodes for data reconstruction based on data correlation between the neighboring nodes. Like for example, if you're trying to measure the soil moisture in a particular area, and suppose the sensor has gone out of work, then of course we can, if there are sensors, neighboring sensors somewhere near the sensor that has that is not working, then we can use the neighboring data to actually reconstruct the data, the missing data. But in that case, there will always be an error, because that is not actual data that you're collecting at that spot where the sensor was to be collecting data. So there are many different ways in which you could do that. We could also use a simple neural network model like LSTM. If you're familiar with long short-term memory models, then you know what's an LSTM. I'll show you the architecture later on. We could use a very simple method also like LSTM, but LSTM model basically is for time series data. So if the sensor is not working because it is going gradually out of battery, then of course maybe we could use LSTM. But sometimes it's not only because of the data fading away. That's called gradual fading. I'll show you the pattern later on, the pattern of missing data, which is called gradual fading, where the sensors go out of battery gradually, and then the data becomes, I mean, there's missing data from that sensor. Okay, so as far as the error is concerned, as you can see from this slide, we have RMSE, the root mean square error of the different methods. So there is a large percentage of root of the error in these kinds of methods. The main goal of this work is to use heterogeneous data and to use a model that can consider both the space as well as the time. So that's why it's called spatio-temporal. Okay, so we consider the spatial characteristics as well as the temporal characteristics. So we need a model where, I mean, which the model can actually consider all the spatial as well as the temporal characteristics of the area, so that we could do very accurate reconstruction. So there are two main goals here. We are trying to use heterogeneous data. By heterogeneous data, we mean that, for example, we can use the soil moisture to reconstruct the rainfall intensity, or to use the rainfall intensity to reconstruct the soil moisture, because these two are related. Okay, so whenever we have related heterogeneous data, we can use that too. Okay, this is the system architecture that we have developed. As you can see from here, at the bottom we have the different sensors, including the rainfall sensor, the soil moisture sensor, the slope gradient sensor, and the slope direction sensor. So these sensors collect data, and then through the coordinator of the wireless sensor network, we send the data to the loss identification module, where we check if there is any data loss. If there is any data loss, then we need to use our proposed deep neural network data prediction module for the actual data compensation. So what we do is we try to predict the data in the future time slots, so that whenever it is missing, we use the predicted results. Then of course we have to ensure that the predicted results is match exactly or very accurately with the actual results. So whenever we have missing data, we use the predicted data. But of course, if we have actual data, we don't use the predicted data. So we use predictions for data compensation or data reconstruction. So that's the main method. Okay, so this is the flow chart of the whole system. As we just said, we start with checking if there is data loss. If there's data loss, we find the missing region, record the time, do the data normalization, and then we use our estimation method, which is called spatial temporal heterogeneous data estimation, and then we try to compensate the data which is missing in the region. Okay, so if there's no data loss, of course, then we store the data directly as the history data, which can be used later on whenever there is missing data. This is the model for long short-term memory prediction. As you can see from here, there are several gates, like the input gate, the forget gate, the output gate. So this is a very famous model which was proposed, I think, more than a decade back. This is LSTM prediction model, which is used very, very often in time series data prediction. So whenever we have time series data, we can, of course, use conventional or traditional models like ARIMA or seasonal ARIMA. Those are the conventional models. But of course, we can also use a deep neural network model like the LSTM prediction model. So this is a very famous model and is very, very popular for doing data predictions whenever the data is time series data. So this is LSTM. As you can see, we have, because of the forget gate, we have the short-term as well as the long-term memory cells. So based on, like, for example, here CT-1 is the memory cell from the previous time slot, and then we are trying to predict the data for the next time slot, that is the CT. Okay, so based on these data, we have different activation functions here, like arctangent activation, and then we have the forget gate, the input gate. So these are all and the output gate. So based on these gates, okay, that is the activation functions, we can actually calculate how much data we want to remember from the past memory cells, and how much data or how much of the data we need to consider from the current data. Okay, so the current data is coming here from IT here. So whenever we have a problem of whether, what kind of trade-off we need to make between the previous data and the current data, then we can use LSTM. So that's why it's called a long short-term memory. So there's long-term memory, there's also short-term memory. So based on this prediction model actually gives a very high accuracy in time series data predictions. Okay, but the model that we have used is convolutional LSTM. If you are familiar with deep neural network models, you know that there's a convolutional neural network model. And actually, this model is a combination of convolutional neural network model as well as the long short-term memory models. Convolutional neural network models, CNN, are basically used for spatial data predictions or object recognition, or any kind of predictions that are of detections that you want to do spatially, like in a 2D image or a 3D image, so 3D video or whatever. So whenever we have data which is spatially distributed along a two-dimensional area or a three-dimensional space, then we can use convolutional neural network model to detect objects, to do all kinds of analysis and image processing or data processing. But here, because we need to consider both the spatial as well as the temporal characteristics, so that's why we use a model which is a combination of convolutional neural network model as well as long short-term memory model. So the long short-term memory model allows us to do temporal considerations. Okay, so the temporal characteristics is being captured by the LSTM prediction model, and the spatial characteristics, like for example the distances between the different soil, the sensors. So the different sensors are distributed over the geographical area, and we use convolutional network neural network models to do the spatial characteristic capturing. Okay, so the spatial characteristics are being captured by the convolutional part of this model, and the temporal characteristics of the data or whatever data we are collecting from the sensors is being captured by the LSTM model. So because we have a combination of convolutional as well as LSTM model, that's why we can capture both the spatial as well as the temporal characteristics of all the data that we are collecting from the sensors. Okay, so this is the actual model that we proposed in this work. As you can see from this diagrammatic representation, there are 4 channels of data here. So we have 4 different colors, like the brown one, the cyan color, the light green one and the yellow one. These are all the four different data that we have collected from the 4 sensors. So here we have a legend here given on the top left of the diagram. We have the soil moisture, which is in, I'm sorry, the spelling is wrong here. The soil moisture is the brown one. The rainfall intensity is the cyan colored one. Slope is the green one, and the slope direction is the yellow one. So okay, so we collect 4 different kinds of data, and we have 4 channels in the input data. But of course, because besides the 4 different data or the 4 channels from each sensor, we also have to consider how many sensors we have in the geographical area. Here we are considering an area of 20 by 20. That is, we have around 400 different sensor data coming from the different sensors. Okay, so basically the input will be of the shape of 20 by 20 by 4. Okay, so 4 is the number of channels. Of course, we have to decide on the architecture of the neural network. In any kind of deep neural network modeling, we always have to, try to explore on what exactly should be the architecture of the neural network model, what should be the different hyperparameters of the neural network model. So this is the research part of the work. So here, as you can see, we have 23 different convolution LSTM blocks. So these are the building blocks in the first layer. We have 23. Of course, you might ask a question: why we are having 23? Why not 21? Why not 24? Of course, we have experimented with all different kinds of the structures, and finally we saw that 23 was giving a very good result. Okay, so that was, of course, that was based on the data that we have for the training part of the model. So basically, we chose an architecture which has 23 building blocks in the first layer, and then we have 23 building blocks in the second layer. So we have 2 layers here of convolutional LSTM blocks, and then we have a third layer which is a convolutional 3D convolutional neural network here. So this is a 3 by 3 by 3 kernel which is in the third layer. We experimented with more than 2 layers. We also experimented with a single layer. The single layer one was not giving a good result, and the 3 layers one was giving a result which was almost as accurate as the 2 layer one. So finally we resorted to this architecture, which gives a good trade-off between the efficiency as well as accuracy of the whole system predictions that we want to do. Okay. So here are the numbers for the kernel size, the filter numbers, the cell numbers, etc. And this is the time that we have spent in training the model when we had different cells. As you can see from here, of course, the number of cells, whenever it is less, like 11, 17, then of course we don't need that much of time. And whenever we have a larger number of cells, of course we need a larger training time. So that's very obvious and very intuitive. But the actual target here is how we can do the. We have to come up with a model which gives a least accuracy, greatest accuracy. Least error. So this is the validation loss, which is the error. So from here you can see 23 blocks gives you an error of 2.11 by 10 to the power of -4. So this is a much smaller error as compared to other architectures. So that's why we settled with 23 number of cells or the building blocks. Okay, then for the whole prediction model, as you can see here, this is a very typical flow chart which is used often for training and testing deep neural network models. So we randomize the weights, we try to compute the network error, and then we adjust the weights by using a gradient descent, and then we try to rerun the whole training process by doing multiple epochs of training. So this is the whole training part of how we came up with the final model for data predictions. And then we, of course, do the testing and make sure that there's no overfitting of the model. So this is a very typical way in which we come up with a good neural network model which is suitable for whatever kinds of predictions that we want to do. Okay, so let me go into the experiments. So that was the whole system design. As far as the experiments are concerned, we developed it on in this environment, we have the Intel CPU and GPU we used GTX 1060, and then that's the memory, the operating system, the programming language we used was Python 3.6.4. Okay, as far as the data is concerned, as we just mentioned in the slide on architecture, we had a grid size of 20 by 20. That is, we have 400 meter data. And we considered each adjacent sensors to be separated by 2 kilometers. The data is actually the real data collected during the time period from April 5, 2013 to October 12, 2017. So that's a span of more than 4 years. So that's a period of 4 years data that we collected for the soil moisture and all the data that we needed. Okay. So the number of samples for training was 22,500 samples, and for testing was 2,250 samples. The data was collected from 7 different stations. So these are the names of the stations. Okay, let me show you the actual geographical map. Then you can have a brief idea of how the data was collected. So we have 7 different stations here which collect data. So actually these are the coordinators, the 7 coordinators which collect data from the 400 sensors. So we try to augment the experiment data from the 7 stations, from 7 to 400 nodes, which means that we have actually 400 nodes here, but we get the data from the 7 stations. And on the right hand side, we can see that whenever we have a more darker area, which means the soil moisture is less. Okay, so here from this area, we can see that on the bottom left, the soil moisture is greater than the area on the top on the top right. Okay, so the bottom left has more moisture than the top right. We use a metric called the root mean squared error, which is quite popular, and I think most of you might also know that. So whenever we have a difference between the predicted result and the actual result, we can collect all the differences here. Y minus Y hat is the difference between the actual data, the original data, soil moisture, and the reconstructed soil moisture. So as far as soil moisture is concerned, but of course we can do it for rainfall data also. Whatever kind of data you want to do predictions, we always collect the differences, square them up, and then take the summation, and finally that's the average, and we take the square root. So that's the root mean squared error, which was used for the evaluation of the whole predictions. Okay. As far as missing data is concerned, we considered 3 different missing data patterns. The first one is random. Okay, so we use random missing data pattern. The second one is gradual fading. Gradual fading means that it was not missing. The data was okay, and then gradually it started missing. Okay, and then of course it kept on missing. Maybe that's because the data was going out of battery, or the data was covered by some soil and it was not doing correct, or it was actually not passing the data through the wireless communication protocol or whatever. So whenever we have data which is gradually missing, that means it's over the temporal axis, then that means it's a gradual fading pattern. We can also have spatial events, like for example, we have a whole area of the soil moisture data which is missing. Sorry. Okay. So like for example, here we can have a whole area on the top right where the soil moisture data is not coming in, or the rainfall data is not coming in, because maybe due to several reasons. One of the reasons could be that the sensors were all washed away by the big rainfall or whatever. So whenever we have these kind of missing data, we can do reconstruction. So these are the 3 different kinds of patterns that we consider. Okay, so this slide shows you that whenever we have random missing data, it looks like this. Okay, so the black ones are the random missing, and the gradual fading, the center one here, as you can see, some of the sensors go out of work and it becomes dark here. And then we have a spatial event. Some portions of the data are missing. Okay, so these are the visual representations of the different missing data patterns. Okay, so we compared our work with linear interpolation, which is very, very often used by researchers or whoever is trying to manage the wireless sensor data. So that is the linear interpolation. And then we have LSTM, which is a very simple, as I just mentioned, it's a very popular model for time series data predictions. So LSTM, we compared it to LSTM model also. So those were the targets of comparison. Okay, we did some evaluations like the random missing data, using the random missing data pattern, evaluation using the gradual fading, the spatial event. So those are the three patterns that we used for evaluation of the accuracy of data predictions or data reconstruction. And then we tried to evaluate the impact of the data reconstruction on the actual landslide prediction. Okay, so this is on the actual landslide prediction, that is the FS value, the factor of safety value, on how much error we are getting for this factor of safety value when the data that is reconstructed has some kind of error. Okay, so whenever there is some error in the reconstructed data, how much does it affect the landslide predictions? Okay, okay, let me go on to the first experiment. This is the random missing data type. So as you can see from here, irrespective of how much missing rate we have, like 10% is a small amount of the data is missing, 90% means a lot, almost all of the data is missing. Okay, so for random missing, as you can see, linear interpolation gives a very bad result. So this is the amount of data, the amount of error in the data. This is the RMSE value, root mean square value. So it is very, very large. So that is not acceptable. The reason it's not acceptable is because, of course, the first reason is because it's the error is too large. The second reason is because of this such a large error in reconstruction, then you won't be able to get a very accurate predictions or the landslide prediction. Okay, so on the final result, you won't be able to get a very good prediction. Okay, let's look at the LSTM predictions. As we can see from here, the LSTM prediction also, the error in the LSTM prediction also increases with the increase in the missing rate. Okay, so this is also something which needs to be considered, because if it increases a lot, like for example from 0.11, 0.13, 14, 15, 16, 17, so it keeps on increasing. This is only for the rainfall data. We might also have errors for the soil moisture, and then when we combine all the errors, and when we do the error propagation, then of course it affects the final result. But when you compare it with the convolutional LSTM, you can see that even if we have a very large missing rate, the convolutional LSTM error, the error from the convolutional LSTM prediction is much smaller as compared to the other methods. So even for 90% missing data, we have a very small error rate of 0.04. This is for the rainfall data in terms of the millimeters of rainfall. Okay, so it's plus or minus 0.04 millimeters of data. Okay, and then for the soil moisture, it's plus or minus 0.02. That's the small error. Okay, but for linear interpolation, for LSTM, that's not good. That's not working very good. So this is in the random missing data. You can use the bar chart to see the amount of data, amount of error that we are getting. The pink one is our method, the computational LSTM based method. The brown one is the LSTM method, and the yellow one is the linear interpolation. So this graph tells you that you should not be using linear interpolation. You should be using some kind of prediction model. You can of course use a traditional model. You can use LSTM model. You can also use convolutional LSTM model. So that was for the rainfall. This is for the soil moisture. So you can see that irrespective of what kind of data, whether it's rainfall or soil moisture, we're getting a very low percentage of the error when we use convolutional LSTM. So from this visual presentation, you can see that whenever we have missing data, this is the second one here, LSTM does some kind of reconstruction, but it is still, there are still lots of data which is not actually matching with the original data. So on the left hand side, we have the original data, and on the right hand side, we have the convolutional LSTM reconstructed data, which actually, when you look with your bare eyes, you can see with your naked eyes, you can see that actually it is matching with the original one. The match is much better than the match between the LSTM result with the original one. So from here we can see that convolutional LSTM actually does a very good job in the random missing data. Now let's look at the different other two missing data patterns. This is for the gradual fading. even for gradual fading, you can see that convolutional LSTM exhibits a very good performance. Okay, so this is for rainfall. This is for soil moisture in with gradual fading. And let's go directly to the visual presentation. So from here you can see we want to have data reconstructed to match the original data here. And convolutional LSTM is the right one, which actually matches quite well with the original one. LSTM does a fairly good job, but you can see that it's still not as good as convolutional LSTM. So LSTM does not do a very good job. We have not put the linear interpolation here because it does not work very well. Okay, and then let's look at the spatial event. Okay, spatial event means a lot of soil moisture. The sensors have gone out of work. So for spatial event, we can see from the bar charts that we are getting a very good result. Okay, so from the visual presentation, you can see that convolutional LSTM, even if we have a lot of the sensors not working, like the dark areas here in the missing pattern, this is the spatial event missing pattern. Convolutional LSTM tries to reconstruct all the data. So from all these three different patterns, we can see that the rainfall reconstruction, rainfall data reconstruction, the soil moisture data reconstruction, we get a large percentage of reduction in the error. Okay, so as compared to the LSTM, the more simpler LSTM model. Okay, so now let's look at the actual impact of the reconstruction data reconstruction on landslide prediction. Because finally, what we are concerned with is the FS values. As we just mentioned, when we have FS less than 1, it means there's a landslide. If it is greater than or equal to 1, then it depends on how near we are to 1. If it is very near 1, then of course it's quite unstable. If it is as large as 2 or 3, then that means there's no landslide. There's no probability of having a landslide. So the critical value here for FS is 1. So if you have an error, which is like for LSTM, when we have 40% missing rate, and we have an error of 1.23, which means your result might be plus or minus 1.23, then you're not sure whether you are going to have a landslide or not. Okay, so then that becomes very difficult to predict, because your error 1.23 is actually the margin of decision. So you need to decide whether you are going to have a landslide or not, and the critical value is 1. Because when FS is less than 1, there's a very big probability of having a landslide. When it is greater than or equal to 1, maybe there's no landslide. But when it is very near 1, it's quite unstable. If it is 2, if it is 3, then that is quite stable. Okay, so 1 is a critical value. So when we have missing data as large as 40% or even more than that, then we are not going to have a very good, a very accurate landslide prediction. But for a convolutional LSTM, as you can see, even if we have 90% missing rate, the error that we are getting is 0.22, which means FS value, whatever we have done for the FS value predictions, the error is plus or minus 0.22. Okay, of course, it's quite large as compared to 1. That means it's more than 22%, but at least it's much better than something which is not reliable as LSTM. Okay. This is for the gradual fading. So I'm sorry, this is for the random missing, and then for the gradual fading is like this. So even here, if it is more than 50% missing data, LSTM cannot be used. Okay, so it's totally unreliable here if it is more than 50%. But for convolutional LSTM, actually we are getting a quite small error here, even in the FS value. This is for the spatial event. Spatial event, as you can see, starting from even 10% missing data, LSTM cannot be used. Okay, so this is 1.33, which means on the FS value, the final prediction will be the error will be plus or minus 1.33. Then because the critical value is 1, it cannot be used. So if we have spatial event data missing, that is the missing pattern is spatial event, actual LSTM cannot be used in any of the missing rate cases. Okay, but for convolutional LSTM, you can see the error is at most 0.22. That is, the FS value is plus or minus 0.22. The error is plus or minus 0.22. Okay, so that is the result of our work. Let me show you the final conclusion. Okay, so this is the reduction we are getting for the FS value, reduction in the error. And then for the whole system, we compared the training time, the GPU usage, and the memory. So you can see that because convolution LSTM model is much more complex than LSTM, of course, then the training time takes a much larger training time, like 14,023 seconds. But of course, this is only a one-time job. Then, of course, this can be done beforehand or prior to the actual landslide prediction. And for GPU usage, we are using a larger percentage than the LSTM, and then we have the memory. Okay, finally, let me conclude the talk. We proposed a spatial temporal heterogeneous data reconstruction system, which is a CPS for landslide prediction. We used convolutional LSTM for very accurate predictions. We worked on the rainfall data, the soil moisture data. We also considered all different kinds of missing data patterns like the random missing, gradual fading, and spatial event. And then, of course, we considered heterogeneous data reconstruction, and we are getting the root mean square error of the FS value is less than 0.3 in all cases, even if the data loss rate is as high as 90%. Okay, thank you very much, and I can take any questions if any. Thank you so much.
Thank you so much, sir. The presentation was really informative and very detailed. I'll check if anyone has any questions and I'll redirect to him.
Thank you, sir, for accepting our invitation as a chief guest and a keynote speaker of the day. So actually, your presentation slides were very impressive, and it was very informative, and it will be definitely useful for all the researchers, and especially those who want to start their research in the area of landslide prediction and deep learning applications. Very, very helpful. And finally, you gave the explanation of the LSTM, convolutional LSTM model. Very impressive and very nice, sir. And once again, thank you for accepting our invitation and join us our session successfully, sir.
Yeah, thank you so much. Thank you so much for the opportunity. And actually, I would like to add that because we have several collaborations with different universities in India, like IIT Ropar, Chitkara University, MIT University, and the different colleges affiliated to the Anna University. So actually, if Easwari Engineering College would like to have any collaborations with the Taiwan universities, including our university, National University, or other universities, we can always get into contact and we can explore future collaborations.
I have one question, sir.
Sure.
There is any opportunity for doing fellowship, sir, postdoctoral fellowship in your university? PDF,
I'm sorry.
Postdoc.
Postdoc, it actually depends on the application itself, because on the different applicants, we need to get a budget from the Ministry of Science and Technology. So if there are any good applicants who would like to do postdocs in Taiwan, in any of the universities, we can always do the applications and try to get a budget from the Ministry of Science and Technology. Yeah. So our ministry is Ministry of Science and Technology.
Collaborate with you, sir. Actually, we are having UG students, sir. That is BTech courses we are having. Can you hear me, sir?
Yeah.
So we are having BTech courses. In what way we can collaborate with you, sir? That is, shall we do one semester with your university or any internship? Are you providing any opportunity for your students?
Yeah, actually, we have lots of internship opportunities here in Taiwan because our Ministry of Education is trying to promote a more deeper exchange and collaborations with universities from Southeast Asia, including India. And actually, we have lots of Indian students coming to Taiwan for internship, like, for example, 2 or 3 months. The longest is 6 months. And these internships are all paid by the Ministry of Education. But because this year, because of the pandemic, all the students who were supposed to be coming to Taiwan, they have not come. So the project has been extended. The internship project or the internship program has been extended to next year, 2021. So if Easwari Engineering College would like to send some students to Taiwan for short-term internships, we can always try to go over the cases and discuss on the actual research topics. Actually, I have a website which gives all the research topics for interns. So if any of the students would like to come, they can do the application directly online, and we can process the application and we can accept the students to the universities in Taiwan. As far as our own university is concerned, National Chongqing University, actually we have, I think, more than 100 seats of internships. So there's a very large opportunity for students to come for 2 or 3 months. Of course, if you would like to have exchange students, that is students coming for 1 semester and doing some courses, then we have to sign an MOU at the university level. That can be discussed with the Office of International Affairs. I can try to connect Easwari Engineering College with our Office of International Affairs, and because we can sign a university level MOU where the students can be exchanged. So whenever we have an exchange of students, the students don't need to pay the tuition fees at the host institution. They only have to pay the tuition fees at the home institution, that is at your university. So they only pay your tuition fees and they can come here for 1 semester, and we will provide the dorm rooms. Actually, we have dormitory on campus, basically they will have to only cover their own living cost. That is for the exchange students.
Really great, sir. So we need the procedure to connect with you, sir. Kindly share with us the website and other details. With the Kanaga Raja, sir, we can get from him.
Yeah, sure. I'll write all the details into an email and I'll send to Dr. Kanaga Subaraja.
Yes.
So we're looking forward, sir, to connect with you. Thank you so much for this opportunity, sir.
Thank you, Dr. Anand.
Thank you, sir. Once again, I will thank you for accepting our invitation as a chief guest and a keynote speaker of the day. Actually, it was a really wonderful speech, sir.
Thank you so much. Yeah, it was my pleasure.
Thank you, sir.